So our last lecture really got into a lot of technical mathematical details. Today's lecture is going to be a little bit different. It's not going to be nearly so grungy. We will be dealing with mathematical concepts, but we'll be dealing really at a much more conceptual level as we get at some deeper issues in terms of the behavior of this new quantity we've been exploring, the electric field. To somewhat summarize where we are so far, we've got a number of key results, and I'd like to kind of put them all into their individual context, or into a greater context, actually. What we've been focused on is the consequences of Coulomb's law and what the forces are that the charges feel, because once we know those forces, we can use everything we know about from Physics 1, from mechanics class, to tell us how those charges are going to move. The question is, what is the force? And we found this very powerful way of deciding what that force should be. The force on any charge Q is this new quantity we've been exploring, the electric field, which is a property of each point in space. You take the electric field at the location of our charge, multiply by the charge, and that gives us the force. So what we've been working on, what we've reduced this question of what are the forces on charges, we've reduced that to a question of what are the electric fields in all of the situations that might interest us. And so what we've been doing bit by bit in our various exercises is actually building up a database of electric fields for a variety of different situations. And our goal moving forward is to create a database of electric fields that we can use to calculate the force on charges in any situation. So let's see how we're going along here on our database. In terms of how we calculate the fields, we calculate them through the sum, which we got from the principle of superposition. We can do it either in the Cartesian form, which is great if we happen to know the coordinates of the charges, or we can do it in this trig form if we happen to know all of the relevant angles. And buried deep within this result is actually the result for one particular scenario, namely the scenario for a single point charge. Because after all, for a single point charge, we just have one term in this sum. We can just copy down the term. It's Coulomb's constant times the charge times the unit vector that points outward from the charge. So here I'll put my little r hat, points that way, outward, divided by the square or the distance r between the charge and the point where we're calculating the electric field. Okay, that's pretty simple. That's just a point charge. The next item in our database, actually, is the electric field from a linear distribution of charge. We take a line and we distribute it. We populate it equally with point charges all along that line, smearing it out into a charge distribution. It has a certain length to it, and we are packing the charges in at a certain amount of charge per unit length, which we call lambda. And then we calculated the electric field above that line at a distance z, and the result that we found was the following. Namely, we've got some prefactor, twice Coulomb's constant. We have a direction, k hat, which is directly outward away from the line of charge, which makes sense. If we have a positive lambda, then the force should be upwards or away from the line. But wherever we're standing, if it's a positive line of charge, we know we'd be just directly repelled from it. So it's outward from the line. It has some prefactors. And the interesting thing, though, is the dependence. Now that we've smeared this point charge out along a line, rather than the field dropping like 1 over r squared, it's now dropping like just 1 over the distance. So we go from 1 over distance squared to 1 over distance as we go from a point to a line. Now on problem set 2, you are asked to calculate a problem where you are calculating the electric field above a disk. And then later in the problem, you are asked actually to consider what happens when the radius r of your disk is moved out towards infinity, by which you then create an infinite sheet of charge. And this gives another very interesting result. When we're above our sheet, the electric field we find has some prefactors, and it's proportional to this quantity sigma, which tells us now the charge not per unit length, but per unit area, because we're spread out over an area. And so we have some prefactor that's proportional to that charge per unit area. The direction of the field, again, is outward from the plate, if the plate happens to be positive. If the plate's negative, the field would be inward, of course. But the really interesting thing is how this depends upon distance. It does not depend upon distance at all. There's no dependence on distance. It's a constant. It does not depend upon z. So we have this interesting trend where for the point charge, the field goes in proportion to 1 over distance squared. For the line of charge, it goes like 1 divided by the distance. And for the sheet of charge, the dependence, when we smear things out yet once again by yet another dimension, the variation with distance is constant. So it's really like 1 over distance to the 0 power. So you can see this trend in the exponents, 2, 1, and 0.